Hey everybody, welcome back. Today we're going to be looking at lesson number 9. So this one's going to cover about probably 3 different videos. And we're going to start off with, in your notes, A, cell notation. So if you take a look here, cell notation is something you've seen, although you didn't realize that's what you were seeing. On the homework from yesterday right here, you'll see this kind of a familiar setup anyway, where there's an anode, then a slash, and then 2 slashes, or sorry, then electrolyte, then 2 slashes, then an electrolyte, slash, and then the cathode. That's essentially exactly how they set up. Well, that's exactly how every cell notation will always look. If it's written properly, it should be the anode on the left, it should be the cathode on the right. And then the electrolyte that goes with each of those electrodes beside them. The double slash in the middle, like it shows in your notes there, is the porous boundary. So that can either represent the porous cup, like we talked about, or it can represent that U-tube, that salt bridge that connects the 2 half cells. So either way, on the separation of that, you've got basically your reduction happening on one side, your oxidation happening on the other, and they have to be separated. So anytime we write this, for example here, given this practice problem, let's take a look at this one. It says, write the cell notation for a copper zinc cell including voltage. So the first thing we got to do is look at, what do I have? So in a copper zinc cell, I know I have copper solid. And in that copper half reaction, I also have copper 2 positive. I have zinc solid, and I have zinc 2 positive. Okay, so if we jump over to our data booklet, you can see copper is right here. There's its half reaction. And zinc is, let's see if I can do this right here on your data booklet. So out of the 2, the copper 2 positive is going to be my SOA. It's higher up on the left side over there. And zinc solid right here is going to be my strongest reducing agent. So if we hop back to here, this is my SOA and this is my SRA. So remember, because that's my strongest oxidizing agent, it's being reduced. If it's being reduced, then essentially what's happening on the copper side is going to be the cathode. And what's happening on the other side, it's the strongest reducing agent, which means it's being oxidized, which makes that side the anode. So since I always start with the anode first, let me color that in here. Since I always start with the anode first, I'm going to start with the zinc. And we always start with the electrode, which means the solid. So in this case, I would start with zinc solid slash its electrolyte, which in this case is zinc 2 positive, is separated from the other side, which is the copper side, which is copper 2 positive and slash copper solid. Okay? Now, the other part to this is, if we go back to the work, if you're looking at your page, you'll notice up at the top, I forgot to point this out, but you have anode electrolyte, electrolyte cathode, and then next to that it says EO net. Okay? So essentially, we also have to write, and it should be to the right of this, although I wrote this too big, you're also going to have the EO net. Now that little degree symbol right there, that just means under standard conditions. So normal atmospheric pressure, normal temperature. It's really not going to change anything. What they're really asking for when they say the EO net or something like that is the net electrical potential, the voltage. What is the voltage this cell can produce? So because, I can go back to my data booklet here. Remember that because we wrote the copper reaction forwards, we would leave that voltage, the positive 0.34. And because we wrote the zinc reaction backwards, we would flip the negative 0.76. and we combine that to give us a positive 1.10 volts. Now normally that would be to the right. Oh, let me go back to my drawing here. Normally that would be to the right of the cell notation, not underneath it. I just ran out of room because I didn't plan very well. Okay, so that's cell notation. So let me do one more for you. Let's say we've got a, what would be a good example? Let's say let's say we have a tin and silver. Let's say we got a tin silver cell. I don't know why you'd make a tin silver battery, but why not? Maybe you just like expensive things. So if you look at back at your data table here, your tin is right here, right? SN solid, SN2. And our silver is much higher. I can't even point quite that high, but just above my finger a little bit at positive 0.80 is the silver reaction. So silver is higher on the left, so it's going to be my SOA. We come back to here, and the tin will be my SRA. Okay, so remember, anode always comes first. So we want to start with what's being oxidized, right? Remember that Leo Anderson is a Gurk. So if we want to start with the anode, we need to start with what's being oxidized, which means I need to start with the reducing agent. Okay? So in this case, that's the tin. So the tin from my half reaction, I'm going to write backwards. So it's tin solid. Oh, let me give myself more room this time so I can write it properly. So SN solid would be the electrode. Its electrolyte is SN2 positive. It's separated from the silver, which is Ag positive, and then Ag solid. Now we need to figure out the voltage. So in this case, the silver reaction we wrote forwards, that's a positive 0.80 volts. And the tin we wrote backwards, so that's going to become a negative 0.15 volts. So that's going to give us 0.65 volts, if I'm doing my math right. And we should put a positive there to make sure that we're showing that properly. Positive 0.65 volts. Okay, so hopefully that makes sense. If you have any questions, let me know. But that's the basics of cell notation.